My name is Bill Pascoli, and I'm a former regional engineer with AISC. And just get a notion as to who's in the audience. This is in the architects track. Are there any architects in the room? Hopefully a few. Oh, wonderful. Two of you? Two of you, wonderful. Okay, good. Okay, now, this is in the architects track. And it's important that the architects write down the PDH code. This is AIA CES approved, so you can get one learning unit, but you'll have to register your attendance at the course here at the conference, and then someone from AISC will contact you, get your AIA number, and then register you online. Okay, and Larry Flynn in the Chicago office will be the one to do that. Thank you, Larry. Okay, so it's AIA approved. Therefore, we have a course description. And I won't read that, but it's going to be on Design Assist. And it more or less covers the description of the course in the program, but it will follow that. Got some specific learning units, and I won't read them intently here, but describe the process of Design Assist, the value of Design Assist to the steel package, channels that tend to hinder communication between the parties, and to determine when to engage the structural steel industry with the fabricators in order to make this beneficial. I'll introduce the speakers. Peter Cheever from Boston, LeMaisure Consultants, and Cameron Baker with Sipple Steel Fabrication in Ambridge, Pennsylvania. So I'll turn it over to Peter, and he'll get started.
Hi, Bill. Thank you, Bill, and welcome everybody. And I should mention, this is probably the only opportunity I'll get. I've done a number of these sessions with Bill. Bill told me yesterday he's retiring after 20 years with AISC. He's going to go on and do some other things. So congratulations, Bill, and good luck. And I also like to thank Cam Baker for agreeing to co-present on this topic with me. In a way, it's sort of bittersweet because we've had a great run doing the building, and this actually represents the end of our work together. But I'm always hopeful we'll get more opportunities to work with Sipple Steel because they're a top-notch fabricator, and it's the first time I've worked with them. But anybody that knows the PNC Tower project in Pittsburgh, I'll put that project up with any job for complexity, and they bang that one out of the park. So, and certainly want to thank all you guys for coming. I know Bill surveyed for architects. I'm just curious what else we have in terms of fabricators. Any fabricators here? Okay. Engineers? Erectors. Wow. Well, we got a good cross section here. It's about all I can ask for. That's great. Anyway, I like to say this project is a fairy tale story, unfortunately, where the owner, the architect, the contractor, and engineer, fabricator, and erector, just about everybody we got represented here, actually collaborated to deliver a really good project for the owner. And, you know, fairy tale story. Why? Unfortunately, if your experience is like mine on a number of projects nowadays, the contractor forces us out to put an early steel package out. Everybody else isn't committed to that early steel package in terms of what's really required. And then there's all sorts of change orders, and there's a lot of finger pointing and everything else like that. On this project, that didn't happen, and I'm hopeful. And a single biggest reason for that, I believe, is because of the design assist process. And that's why we really want to start talking about it, because we can't promote it just as engineers. We need fabricators to be promoting it. We need erectors to be promoting it. We need the general contractors to be promoting it. So just a brief outline of what we want to try to cover here. I'll give you a project description, the members of our team, the basic structural design of the building, the bid process for Design Assist, which is pretty unique. Cam will go through that with you. And then we'll get into a little bit of what was actually going on during the design assist process, and, you know, things that you do on every project, but why was it different and what was the same during the design assist in terms of designs phase, shop drawing phase, the fabrication phase, and then the construction phase. And then, of course, we'll go through briefly lessons learned. So project description, just to give you a basic idea of the location. So Cleveland downtown is right off Lake Erie, as you well know. So the clinic itself is about 5-6 miles to the east. And, you know, it's an entire campus. They have a huge campus there, and they also have satellite campuses. So one thing we learned early on is the clinic is a very sophisticated client, and they were the ones that brought this idea of lean construction and the design assist process. And, you know, I've gone to some other presentations here at the conference, specifically the one on Washington U, where they were using the 3D BIM, and they were sort of at the leading edge for submitting shop drawings. And again, that was a client in the medical field. So it seems like these institutional clients, they've really thought it out and understand they need to do team building. They need to, it isn't always just low bid. And in fact, I say that reinforces why our own practice, we're heavily weighted into the institutional client field, because they are more enlightened and they have better schedules, better funding, so on and so forth. But anyway, this could be yet another step that I think to try to bring to other projects and other types of owners so that they can see the benefit. And just to show you the overall site of our building, we're right in the heart of the campus. And there's a master plan being done actually by Renzo Piano that creates this green mall running down the center of the campus right here. And then this is Carnegie Avenue, which is the main drive, accessing the rest of the site. So the whole drive up, drop off, the way that they envision it here, and then maintaining this landscape mall sort of constrained the building in terms of the footprint they needed, the square footage they were trying to get in, and also the building height. This results actually in the building wind up, as you see, we get into the design, that we're going to actually overhang the building over the drive-up entrance. So this is, it's a 6-story building, but it's got a full penthouse on top of it, 7th floor, and covers the entire footprint of the building. And that's because, you know, these types of buildings, if you worked on these hospital-type buildings, you know there's a tremendous amount of mechanical equipment, mechanical systems. It drives a lot of the design. There's also a full basement under the entire footprint of the building, and it extends under the drive-up. There's tunnels from that leading to the adjoining cryo building. There's also a pedestrian bridge. This is about 377,000 square feet at a construction cost of $276 million. And Sipple supplied 3,000 tons of steel. We checked that yesterday, right, Cam? And 3,100 pieces. So here's just the overall footprint now. You can see it in context. So building footprint is here. We've got a 32-foot overhang over the drive-up. The basement extends out in here, and there's treatment space in there. And then we've got the pedestrian bridge over here to the adjoining building. And then we have the tunnel to Cryle over here. And again, this is the landscape mall. And here's just a transverse section. And you can see here's the 32-foot overhang. Here's the drop off of Carnegie Avenue. Here we've got the treatment spaces down here. You can see we've got thickened walls, thickened slab to protect the spaces where they're doing the treatment. And then here's just a longitudinal section in the other direction. And again, pedestrian bridge and treatment spaces. Within the drive-up, they've put in a few skylights just to try to get some natural light so that the patients, when they go to the treatment space, don't feel like, you know, they're in a dark tunnel space, just to liven it up a little. The team, as we already mentioned, the owner is the Cleveland Clinic. And then there's two architects. There's a design architect, William Ron Associates from Boston. They're a longtime client of ours. And then the architect of record is Stantec. And as you know, Stantec is one of these firms that's bought up a number of firms. The real architect doing the work was the former Anchin Allen out in San Francisco. They've done a lot of healthcare work. William Rahn had never done a hospital building before, but the clinic aspires for very good design, and William Rahn Associates is like one of the top 10 architects in the country every year, at least as rated by Architecture Magazine. Contractor is Turner Construction, right from Cleveland. They've had a long-term presence there. In fact, I worked with them there 30 years ago. Engineer LeMessurier, fabricator Sipple Steel, and the erector was Industrial First from right there in Cleveland, Ohio, and they had done other work on the campus. So very early in the project, the owner said, hey, we want to have this lean construction. So how many people here have gone to a lean construction workshop? So, you know, maybe 5% of the people here, 10%. So, you know, this is a 8-hour all-day thing. It's led by a lean construction expert, and you know, everybody goes in there with, and all the designers and all the major, not just the contractor, but all the major trades were there. This is probably like 75 people, and it's just to get people working together and try to have more of a teamwork approach to things. And you know, it sounds so simple, and we talk about these things every day, yet if you reflect on your own work, I'm sure if your experience is like mine, there are all these projects that for whatever reason that doesn't happen. But certainly when you find the owner trying to make that happen right from the top, that does have a way of filtering down, and the general contractor is pushing it, and you know, people are willing to get a little more committed and not just trying to protect their own turf. So and I know Cam's associate, Joe McKendry, he was there. It's the first time that I got to meet him. And in fact, we were in the same group. And, you know, I think we both left with a little bit. He said, oh, this is, you know, kumbaya and everything else. You know, we've been through this all in 4 other different contexts. But it really did play out, and it's a good experience. So just to put in context the basic design of the building, this is the architectural plan, and you know, it's basically, if you recall, the mall is over in here, so the patient rooms are going to be here, and the idea is that they're not looking at an urban landscape. They're going to have, you know, a green area that they're looking at when they're in these rooms. And then we've got the core area. We've got all the vertical circulation, stairs, elevators, and all these tremendous mechanical systems. And then the rest of the footprint is examination and administration spaces. So we've done many, many projects with William Rahn Associates in Boston, and they've never met a column they didn't want to move at least once. But the good thing is we have Stantec on board, and they've designed many, many medical facilities, and they know that, you know, we have to have this module. So early on, they established this 32-foot by 32-foot module, and you'll see how that plays out in the framing plan. So here we've got 32 by 32. There's 11 bays in this direction for a length of 352 feet, and then 4 bays in this direction for 128 feet. The core, vertical circulation core, affords excellent opportunity for us also to put some braced frames in here. So we've basically got 6 frames in each direction. Very efficient. We're going to be constrained to W18 beams and W24 girders in order to maintain the floor-to-floor height, but those are economical depths for the spans that we're looking at, 32 feet. And then we're going to use a 3-inch 18-gauge deck plus, we'll start with 18-gauge deck and 4.5-inch normal weight concrete. Cleveland is sort of a border town for using lightweight concrete, but in this case here, we want a 2-hour fire rating, and we're going to go to the normal weight because the added mass is also good for floor vibrations, which is an issue in these types of buildings. So this just shows you the layout for the bracing. This would be along the line B. And you can see also on this section, I'm also getting to the fact you in Cleveland, you know, you're not that far from the lake. So we're actually about 12 feet below the water table. So the entire building is going to have a pressure mat underneath it. And And this is just our braced frames in the other direction, in the short direction. Again, those are 32-foot bays and pretty much go from top to bottom. And then lastly, this is our signature feature. The building's going to have a 32-foot overhang so that the driver can come right in underneath it. So how are we going to do that? The architect couldn't accommodate any sort of depth or anything else here. So we said, well, let's go up to the penthouse and we'll hang this. That could easily be integrated with all the mechanical equipment up there. Certainly a 24-foot deep truss is going to be very efficient for transferring 7 stories of load. And it definitely added tonnage to the overall project, but not a huge hit. And certainly for the drama of to get a 32-foot cantilever, it's relatively efficient. So this is just the statics. It's pretty basic. I remember drawing this diagram when I was going out to the first meeting. We've just got the hanger pulls down here, so we just have to balance it, the teeter-totter that it is, and we just need to push back up here on the other column. Now, this does get into the foundations and some other things, because if if that column has P, then all the interior columns typically have 2P. But if I add 2P, now I've got 4P on that column, as compared to this is 2P minus P, so it's only P. So on a mat foundation, you need to be mindful of that. But in concept, it's a very simple approach to a fairly dramatic architectural feature. So I think I'll turn it over to Cam now. He'll talk about the bid process during the design assist, and we'll go from there.
Thanks, Pete. So Pete described the job as a fairy tale. So there's always a villain in the fairy tale. We're still trying to figure out who that is. And typically in an AISC seminar, we're going to say it was the architect. But there's architects in the room, so we can't say that. So maybe we'll pin it on the concrete guy. The concrete guy was the villain. In all seriousness, the job didn't really have a villain. It was a very collaborative environment from the start to the end. And I credit an engineer who's open to talking about other ideas, other ways to skin the cat. That doesn't happen on every project, as Pete said. So the DA process for us starts at the bid level, and I'm the structural engineer for Simple Steel Fab. I worked for a number of years in consulting, so I speak engineer. So anytime our estimators see a strange item in the specifications or a strange item in the bids, they typically bring that to me before we bid the job and say, "What's this all about?" And when they brought the DA bid forms into my office and what is this all about? I had to do some research because I had never worked on a DA project. And I don't think, we had done DA projects as a company, but nothing that was quite like this. So I think as a fabricator, from the fabricator's perspective, when you get that bid form that calls a job a design assist, you have to start thinking about what that's going to entail for you. And every job is going to be a little bit different. I think our idea when we first read the bid forms was, okay, it's going to be like a weekly meeting, coordination meeting, and that's going to be about it. And it really was a much more involved process on this project. I think that in the pre-bid and talking with the design team, we got a better grasp of what was really going to be required. In our specific bid forms, we had to identify who the engineering staff were going to be, what technical assets were going to be brought to the project by the fabricator to assist the design team. We had to outline the hours that we plan to spend helping do, I'll say, just-in-time pricing. We had to be able to provide very quick feedback on a multiple of options to solve a certain problem so that the entire team can make a decision about how we go forward on something that was undecided, or if we want to try to capture value for the owner. There also was a BIM component that dovetailed with the DA process. Most projects now have a BIM deliverable at some point for clash detection between follow-on trades. However, on this job, because of Pete had shown the teeter-totter, there was a lot of connection joinery that was going to happen on that mechanical level. And being a mechanical level, there's a lot of ductwork, piping, and other equipment that has to be coordinated. So we had an early, I'm going to call it a pre-construction BIM deliverable which was a model that had all that connection material already in, but it had to be delivered before our detailing was done. So we had to have this kind of accelerated preliminary model that had that connected information that went to the architect, not to the general contractors. That's a little bit of a wrinkle. We don't typically send something back to a Revit model to be used by the design team. So that was a little bit of a wrinkle. It wasn't an issue, but we did have to plan for that in our detailing process. The execution of the BIM, once we were awarded, there were weekly meetings. That was one aspect of it. Each week there was a laundry list of items that we were adding to every week and taking items off every week. Pete was the champion. The measure was a champion for the meeting, and so they were kind of running the show. But as a team, we had a lot of multifaceted items that had to be dealt with across various trades that might impact follow-on trades. So we were constantly breaking out during the week and having phone calls and go-to meetings just between LeMessurier and Sipple, between Sipple and Turner, to try to resolve some specific issue. And then every week there was a lot of pressure to bring a solution to what you talked about last week, because you didn't want to be the guy who said didn't do anything on that this week. So we had to integrate both the engineering solution, okay, so how we're actually going to do it and satisfy the design constraints and all of the design side issues. We also had to have the costing associated with that solution so that they could take to the owner one or two or three options to choose between. This is a little blow up. It shows just kind of the documentation that followed on week to week. And like I said, there was a responsibility. There was, everyone talks about action items, and well, the action items were always identified, and there was always a lot of pressure to come up with a closing. So the other thing that happened all through the project, this owner, as Pete said, is very sophisticated. They actually have parallel projects going on, some in different modes. Design build was in one of the modes. There was also a design bid build, all going on at the same time. Our job was one of three that were in some phase of design to construction. They track specific metrics all through the project to identify how effective the team is, and they evaluate you every few months. You get an update on how you're doing. This particular graphic that we're showing is a plot of where we are, the GMP versus the current budget forecast versus the target budget forecast. You'll see we're always above the GMP. That's because there's obvious scope changes during the project, and the owner's agreeing to those scope changes as we go on. And then at the end, we kind of split away a little bit, and our forecast is higher than our budget, and that's because we are actually at that point in the project capturing value where it's costing the owner something more in our contract, but there's a follow-on trade whose credit is bigger than our cost, and so the overall project, the price is going down, even though our price is going up. We're going to go through a few examples here and specific ideas and ways that we use the design assist process to capture value for the project and to increase the performance of the project. One of the items at the design level or at the bid level, the project showed a 18 gauge 3-inch deck. Pete talked about the lightweight concrete. I think we had 10-foot spans on our deck. And so, immediately we jump in there with, hey, we got a cost a VE item. We can go a 20 gauge deck. And there was some back and forth about how what would happen there. Pete identified something that we didn't know, or LeMessurier identified something we didn't know about early on hospital projects because of the number of penetrations through the floor and the number of hangers that they are going to need. They were concerned about the deck gauge going down to 20, having some issues during the construction phase of pulling those anchors through the floor, through the decking. So the problem that we had was that the 18 gauge deck was not erectable in 3 spans by iron workers. They would have to have a crane if they wanted to use 3-span deck at 18 gauge. So we were able to find a common ground at 19 gauge 3-span that allowed, there's some cost savings for the material, obviously, and then there was a schedule impact that we were able to maintain the schedule we predicted because the iron workers could shake the deck out by hand, and I had to have a crane to do that. Here's just some pictures. So you can see on the right-hand side there, it looks like we have chicken pox on our deck with all the hanger tabs coming through. They're all color-coded, you can see in that picture, and we're going to talk probably at the end, a little further on, about the coordination at the NEP level and all the sleeves. They actually use that color coding to identify the different trades, whose hangers were whose, and there were quite a few sleeves used to help the project without having to do the coring after concrete was placed. Last I'm going to talk about on the front end here is some of the scope changes that happen. Now, this is a structural steel conference, but miscellaneous metals are still part of our world. Stairs are still part of our world. When the job was bid, the stairs were specifically identified as commercial grade egress stairs, and that's how the job was bid. Once we got into the DA phase of the project, we found out that the owner's idea of what these stairs were going to look like was different from what the contractor had thought when he wrote the bid forms. This owner specifically put signage up in their hospital saying, we have free workout equipment, and they have an arrow and a sign to the stairs. They actually want to use the stairs. In fact, the two main egress stairs have curtain wall from the ground to the roof, so they want the stairs to be aesthetically pleasing. And so when we bid the job, we have a certain assumption about the NOMA requirements and about the finish of the stairs. And when that changes, there's a cost associated with that. But the owner was so committed to enhancing the performance, the aesthetics of the stairs, that they were willing to find a compromise position where they paid a little more and they got a better product. And we actually fine-tuned the specification with the architect on how we would use NOMA. We didn't use like a NOMA 1 everywhere. We selectively used NOMA 1 and NOMA 2 in different locations to provide the aesthetic that they want. I have a few pictures here. This screen's kind of small, so you probably can't see it. But the stairs we actually hung on the building, I would say they're probably one of the best set of stairs our company has ever put up, because we really understood what the architect wanted. Everybody came together, including the erector, to put together a really nice product because it was identified by the owner as being something that they really wanted. So just an example of how you can use that collaborative process between the architect and in this case it was the architect and the fabricator to enhance the project. Even though there's a cost increase, the owner's getting what he wants. Pete's going to talk a little bit about some of the design considerations for floor vibration.
This will be quick. There was one thing that was a little stumbling block early on in the project. As I mentioned, these types of buildings, you have to be sensitive about floor vibration, especially in the treatment areas and also in the patient rooms. So early on, we had sort of in the bid set, which actually was just a schematic design set of drawings that we issued. That was what SIPL's base contract was based on. As you saw, we had the W18s and the W24 girders. So we were using a vibration criteria of 4,000 microinch per second for moderate walking speed, which in AISC Design Guide 11 is about 75 steps per minute. So then the clinic had a consultant, and this consultant was fairly well versed in floor vibrations. And there's another guideline in the National Health Facilities Guidelines, and the walking speeds in that are a little different. So there's some gray area in there. And then he had gone out and done some of his own testing of how fast he walked, and he decided that all guidelines should be at the speed that he walked. So anyway, this is the Chinese menu that we prepared, which I'm sorry you can't see from there, but you just take my word for it. There's about, 22 different options there that'll get you to different microinches per second for different walking speeds. But also there are depth limitations, and for certain depths, they were going to have to increase the floor-to-floor height of the building. That was going to add cost in terms of the exterior wall. So, but again, being in this environment where everybody was already on board, that we could collaborate in the solution, including, how nice is it to have the erector on board during the design phase and attend week-to-week meetings actually, happily. These guys participated. So similarly here, the curtain wall guy is already on board, general contractor. We're able to do all this pricing very quickly. And at the end of the day, our baseline that had been on the drawings, like I mentioned, was 4,000 microinch per second at moderate walking speed. So we agreed to and you can see what we had there. So the final design that we went up to 100 steps per minute, which does have quite an increase. The net result was going to a 21 by 50 and a 27 by 84. They did not have to change the floor-to-floor height of the building. It added about 0.7 pounds a square foot, and it was purely a material cost. And again, since SIPL had already submitted how everything would be priced, the owner already knew how that was going to all map out. So this resolution was made without any real contention. And, they certainly got a better value in the building and what they've got there. Whether they, really needed that, that's a whole separate question. So, shall I take this one? All we're trying to do is map through some examples for you, because you're going to sit there and say, okay, what was so different about the design assist process? So we're just trying to provide you with some examples of that, and try to make sure that we articulate who is involved in the conversations as well. So, as most of you that are engineers in the room know, you design your first floor with these deep basement walls, and you have huge soil forces that you've got to resist, and you're relying on the concrete slab to do that. And then in our case as well, we didn't want to run all our bracing down into the basement, so we were only running some of it, and then the rest of the lateral load we're going to drag out through the slab and tie it into the perimeter foundation walls. So at some stage, we start to talk with the architect about how this huge floor-to-floor height, first floor is 22 feet to the second floor, and they're going to have these huge glass walls, how they're going to heat and cool that. So it starts to come out that there's going to be this pipe trench around the perimeter. So any of you that have dealt with this before, so all along the perimeter foundation wall, we're tied into the foundation, into the floor slab. Now we've suddenly got basically a gap. So here's the wall here with probably 7 kips per foot of lateral load on it, and then we've got to try and get it tied into the slab up here. But then we've got this pipe trench. So in our original design, once this started to come out, we had a concrete corbel coming up off here. So we were just going to build a concrete corbel off the wall, and then this little knee wall was going to get formed to sit on it. Well, the concrete contractor, which was also a design assist process, but we weren't the champion on that one. I think the architect was running that one. They did not want to form this corbel, and they had the numbers to back it up. It's going to be 150, 200 grand, but the bottom line was they just did not want to do it. So what I liked about our team and our collaborative process, our guys heard about this, and when I say our guys, I'm talking about the erector, I'm talking about Cam and SIPL, and they said, well, maybe we can solve it another way with the steel. So originally, I remember Cam said, you know what, we'll design the connections from the steel beams into the plate to take all that load. I said, all right, let's have at it. So then I think after a few rounds of computations and realizing how big those loads were, it was probably not the best idea. But then we came up with a way to get concrete to do the work, but a way to do it without any foam work. So I think I have a better, yeah, we have a blow up here. So now what we're doing is we add in a little W8 here to support that concrete, and then we're putting in a little 1/8" closure piece in here. So now all that steel can get put in, and this can all be poured with the first floor concrete. And I definitely recall, not only was SIPL, but the erector definitely participated in this and said, no, we can use a piece of closure and we can erect that like that. And so it really was it was sort of, we collaborated and said, hey, the concrete guy can do it, we'll do it. Now, AISC, we should get an award for that, Bill, don't you think? And, but anyway, and so if you can, I don't know if you can quite see, what doesn't show up in this picture, there's all these pipe sleeves, by the way, that have to go through this to get into the trench. You sort of see them here. This is your pride and joy here.
So the original design for the connections at the teeter-totter called for plates sandwiched on each side of the connections, and I think there was some back and forth between LeMessurier and our office about if that was the best solution to the problem. I think eventually we did zero in on a kind of a hybrid between what LeMessurier had and a more constructible option. One of the problems in this connection, and we're going to get into the erection considerations in a few minutes. Operator error here. So you'll see here that the way this is laid out, this is the hanger. This item right here is in tension, dropping down 5 stories to pick up floors below. And the issue here is that the connection of this element is made 15 or 20 feet off of the floor. So the erector's got a problem where he's got a very heavy strut member. Okay, it's a strut and a tie. So the strut member is very heavy. He's going to have to bring that part in and set it down on top of this little. And these were actually W10s. They were a little thin, and he's going to set this 24 hundreds of pounds a foot on top of this little W10. Then he's got to climb the iron and stuff bolts. So that's a little complicated, and it introduces some safety concerns for us. So while these connections over here pretty much looked in the final arrangement the way they were on the design drawings, we had to make some changes here to make it more constructible. So these are some screen captures from our Revit model. This is looking pretty much like what's happening here. It was a delegated design, so we were designing those connections, and we're going to get into that a little bit later on some of the other aspects of the erection procedure and modifications that we had to make. But here, what we did instead was we wanted to erect the building conventionally on shoring, which meant that we wanted to be able to put that column up and frame into it conventionally, and have the erector be able to work 4 feet off of the ground the way he always does. So what we ended up doing was actually extending this column through the connection and putting a cap plate. We did have a compatibility issue with width because this is a W10 and these are W14 3 somethings. I can't remember where they were, 370. So these were much wider than the W10, so we had to pad some things out. But at the end of the day, it made for a more erectable connection. So these are now the erection considerations. Pete rightly points out that the Code of Standard Practice, if you have anything that's not conventional with your erection procedures or shoring or bracing that's required, it needs to be articulated on the design drawing so that the fabricator and the erector can adequately capture that value in their bid. And we did that on this project. We recognized that from the beginning that we wanted to erect it conventionally. So we had to make some allowances for how we were going to shore the building from that first floor to the second floor so that we could put the final steel on top of that shoring. Here's a graphic that shows 2 options that LeMessurier outlined in the design drawings. One would be to erect a building from the ground to the roof and exclude the hung portion and then come back underneath and erect the hung portion. The other option was to erect conventionally on a shore, and there's a shore that would be needed here, a shoring system that would be needed here to hold those loads during the erection process. So there's a temporary shore. This is the option that we selected. So I'm not going to read this word for word, but the basic erection sequence that we used was to establish. Now, the other aspect that Pete hasn't talked about yet is that they wanted the end of that teeter-totter to be cambered. They wanted it to come down. As they placed the levels of concrete flat work, they wanted the building to come closer and closer to level, or to flat. They didn't want it to have all the deformations under dead load, and so have the floor be at the end of the cantilever lower than actually they wanted it to be slightly positive when we were done. So the first thing we did was to establish what the unloaded cambered shape would look like. Then we would erect a conventional shoring system, and the steel would go up as any other steel job would. After the erection was complete, we would be able to adjust that final camber. So there was a target camber. We established an idea of where we wanted that steel to start when we started the erection. But at the end, we wanted to be able to touch up that camber and dial it in to a tight tolerance, because the measures model was measuring deflections in 1/16 of an inch. We needed to provide that kind of adjustability at the end. After that touch-up was done, we would fully tension slip critical bolts in oversized holes, remove the shoring, and survey under self-weight. And then this is kind of unique to this project. I've never actually measured deformations in service as an engineer. I've never gone back to a building and over time measured the deformations as you put more and more levels of concrete on. We actually surveyed the building after each level of flatwork concrete so that we could correlate the predicted deflections to the actual deflections. The result of that was we were within 3/16 of the engineer's predictions. We had a couple of outliers for some other reasons, but the correlation was very closely matched to the analysis model. So this shows how this is a blow up of our erection shoring plan. So we had some conventional steel columns with some bracing. This is the jack box here, and we're going to talk about this in a second with how we actually put shims in here to create the initial camber, and then we had a hydraulic jack that we could use to touch the camber up and to adjust it within a 1/16 where we wanted to start. So now we're going to get starting in. This is a slide that shows the predicted deflections versus the cambered. So we're kind of changing gears from erection considerations to get into the actual how we achieve the camber. So these are actual design drawings. We actually got a design drawing that had all of the deflections at each stage of the project. So this shows the reason that there's 8 or 10 of those on the building is you have the self weight of the steel, the shored, the self weight, each level of concrete. They actually laid out the deflections of the building at each stage of concrete placement. So this is a blow up. It shows, and the purple that's superimposed are the adjustments that we made to lengths to get the camber. So the camber profile was identified on the design drawings. We knew on day one that we had to provide a vertical camber above normal at that top level, at all the levels. So we proposed a 2-stage process to achieve that. So we made a macro adjustment. So at the time of detailing, we actually adjusted the lengths of tension and compression members to create that cambered profile. And then after we erected the building, we had a micro adjustment with the jack, and we used the oversized bolts, the oversized holes and slip critical bolts to create that micro adjustment for the erector in the field. And as I said, we followed on with verification and observation and documentation as the levels of concrete were placed. So here I got a couple of slides just to kind of show what we did. So this is a drawing this is how we started out. We went through and did basic structural analysis to figure out the elongations and the compressions that we thought the deformations under compression. So here's the schematic. So you have a compression member you're going to lengthen those columns. You have tension members and you're going to shorten those elements. And then we had the micro adjustment. So this is a blow up of our jack box. So we basically had a fixed column that we reused. So we had to come up with a solution. We wanted to be able to reuse that shoring as we went down the building. Of course, the steel's going up and down as we go along the building because, as Pete showed, there was some lowered areas where they had linac and they needed to have skylights. In some locations, we had a linac cap. We actually had a concrete vault cap, 4-foot thick vault cap, and our shore had to sit on top of that. So we basically made up a consistent column, and then we came back with little stools to fill in the gap if we needed to. And then the jack box and the shore were reused from location to location. And then this shows the hydraulic jack sits in here, and these are the shim packs. And we had a 5-page outline for the erector about how to the order of how he did this. Take these bolts out, do the whole process. We actually had base plates on all of these columns that are actually hangers. There's a base plate on here that lives there forever, but it's really just here to connect the jack box. So here's a picture from construction. So here's the jack box. Here's the column, and there's some bracing in here. The bracing and the shoring was a delegated design, so we were given the loads that were anticipated during construction under self-weight. We had to estimate some construction live loads, and we took responsibility for the design of that shoring. That just highlights the elements. And again, that's what the connection looked like. So again, here's the okay. So this is the other element that was identified late in the game. That was temporary bracing on grid line D. So this element here, this is the fulcrum of the teeter-totter, right? It's in a compression, and most projects, as you're placing levels of concrete, you're loading your columns as you go up the building. In this project, as you're placing levels of concrete here, you're loading the column up here. We have a stability problem. We identified early on that the decking was not going to be adequate to brace this column as it was loaded with these levels of concrete. So LeMessurier gave us a set of staged axial loads in the column. So we knew under shored, self-weight, and each level of concrete what the applied loads in the column, or the anticipated applied loads in the column for the concrete and the 20 pounds of construction live load would be. And then again, as a delegated design, we were asked to provide, this is a blow up here showing, this is the first stage, this is the cambered or shored condition, and you see they've shown some bracing here that's going to be needed to brace this column so it can't buckle out of plane. They gave us, these are the actual axial loads, and we took those loads. Here's a blow up that shows the stage at the fourth level of concrete being placed. And we provided, this is a drawing that we produced that shows when the bracing can be removed. That was the other thing that was happening here at the same time, is that the concrete contractor was following on and wanting to remove the bracing so they could start follow-on trades after him. So we actually had this document that showed what dates they could remove the shoring once the concrete levels had reached adequate strength to brace the column. And you'll see here, it also had to be some kind of a bolted connection that could be removed. This gusset had to be cut off, and the erector had to come back after the concrete was complete and get that member out. So the shop drawing process was a little bit different than a normal project. We generated 38 RFIs on this project, which I think is a pretty good number considering the size of the job. The reason we were able to do that is because of the open communication that was desired by the owner. We would solve our differences offline, and then we didn't even need an RFI. We just went with a submittal that had what they wanted on it, and that was the end of it. The key here is to have an owner that wants you to communicate directly between the design team and the construction team. I don't think that happens on every project. And again, because we were able at the front end to solve our differences, there was a much shorter shop drawing duration. The review period was much shorter. So we would follow up. We would have this is one of the connection standards that we sent that shows how we were going to. But everything that's in here that's a change from the design drawings was already agreed upon. This wasn't like a new idea that took another 2 or 3 weeks to review. And instead of sending 3 shop drawings to show this big change, we would start out with what AISC calls substantiating connection design, some kind of drawings before shop drawings, so that everybody understands what the rules of the road are going to be, including the detailer. So the fabrication process in a DA is essentially the same as a design bid build. There really isn't anything different. I will say that LeMessurier's elegant solution to the complicated problem made the fabrication a little bit uninteresting. I mean, it was pretty standard run-of-the-mill stuff for our shop. I will say though that because LeMessurier opened the curtain a little bit and let us see, because they provided the loads on their design drawings, the deformations, we really had a clear understanding of how they analyzed the building and what their expectations were of its performance. So because of that, right after the fabrication process, we're in the erection process, we identified, we have a live construction cam, and our PM came to me one day on Friday and said, they're having a hard time getting this one beam into the strut and tie. You come look at this. So we watched them for a few minutes, and it hit me like a ton of bricks that we had made a little bit of an error in how we thought that deformed shape was going to behave. So I'm going to go back to a drawing I showed a few minutes ago. So this was our cambered diagram that kind of started our thinking about how we were going to direct our detailer to shorten the length of members. We didn't give him this. We actually just told him on your drawings, your paper drawings, after you create your SDS2 model, you're going to shorten these members by this much, you're going to lengthen these members by this much. But this was our internal drawing about how we understood that to behave. There's an interesting thing here I'm going to show. There's a whole half of a building back here that's on this side. And the way the job was sequenced, that was erected, completed, rattled, deck was being shook out, and we were turning over some of those levels to follow on trades as we were erecting this southern half of the building. So that means that this deformation right here is not really accommodated in our connection detailing. And that afternoon when we saw that construction cam, it was like a light bulb went on. But because we understood what the expectations were and what the analysis was on the design side, we were able to very quickly find a solution. So that afternoon, we drafted a sketch to repair the beams. We had the erector put the beams that he already had on site that were going to be following on in that same sequence on trucks, brought them back to our shop. We shortened the members by an appropriate amount. We created a bolted connection that would slip, and then the fabricator was able to shorten the length of the member, get it into that space, load all of the concrete, then we went back and tensioned the bolts in that connection. But we would never have been able to understand what was happening there if we didn't have a DA process where we understood all the behaviors and the expected behaviors of the building. So this is a real success story for, this would typically be a call to the engineer of record. What the heck's going on? I can't get this beam in. They were literally pounding it in with a sledgehammer. So this would typically slow the job down, stop the erector. We didn't miss any erection. We didn't miss an hour because of this problem. So I'm going to let Pete take over now and go through kind of the construction phase.
Yeah, so just a few photos during construction. This is January in Cleveland. Guess what? It's snowing, and we're trying to put our foundations in. But it's complete tied back excavation down at least 30 feet. And this is just 4 months after the steel bid was awarded, and the concrete for that matter. Now it's March, and they've got the hole completely excavated. And if you're familiar with, if you've done mat slab jobs and you're doing a hospital job where you have a lot of below grade utilities, you really don't want to be embedding them all in the mat because it can compromise your structural strength with all the sleeves, and also if you ever have to get back at them, there's no way to get at them. So we've got our structural mat, and then we've got like 18 inches of crushed stone, and then we have a slab on grade on top of that, and therefore all the utilities can run in that space. And I'll just mention something else about that later as it relates to the crushed stone. So here we are, we've started steel, I think it was at the end of April, right? Just about 3 years ago, and 2 years ago, sorry. 7 months after bid. Now keep in mind, that bid was made with a set of schematic structural drawings. And we've pushed it all the way to here where we've actually got steel on site. And I believe the architects' 100% CDs were being issued around the same time when we started steel erection. So we didn't talk too much about some of the DA items that were gone over as it relates to erection a little bit, but believe me when I tell you, they were very active participants. I think they kind of liked the office scenario once in a while. And so anyway, here you see, and we didn't describe this too much, but what we're doing is the west half of the building is being erected all the way to the top, and you can see there's two cranes. one to the north and one to the south here, and they've erected just the first 2 bays. So this would be A to B to C line, and then we'll go C to D to E line. E line is where the cantilever. Here's all that Linac space below grade being started here. So you can see the north crane has erected the north 2 bays, and now it's just started to move down here, and it's going to start working on the east half of the building. So the contractor's original scheme for how to erect this building, Turner Super, was they were going to take all the crushed stone that was down in here for the slab on grade, and they were going to build a ramp down into the bottom of the hole. And then the crane was going to be positioned in the hole. That was the only way they could figure out how to make the picks. You know, if you recall, the building's 350 feet long. You just, you know, you're not going to be able to get to every location with the weight of the picks and everything else. So our erectors dug in very early on the project, collaborated with the supportive excavation people who were designing the supportive excavation at the time. How close can we get? Can we do it? So this 2 crane scheme, they said the only thing is we can do the 2 cranes, but we got to be able to erect the building vertically, not in the more traditional manner where, you know, you're doing plate by plate by plate. And this comes into play in the construction staging that Cam described how we shore the we put the temporary shore in here along the E line. You can see there's the jacking box that he was talking about. And you can see this is only the first vertical, the western half of the building. We haven't done the eastern half. So as soon as they get this all topped out and the trusses are tied together, we remove these and then start removing the concrete. Well, from a mechanical coordination point of view and everything, even though we're erecting vertically, all the coordination is going on more in a horizontal sort of phase. And then, of course, the contractor is tweaking his schedule. Oh yeah, we're committed. We're going to follow you right up. If you erect vertically, we'll pour out concrete vertically. And that lasted for a while until they got spoiled, basically, by us always accommodating them. Us, when I say us, I mean us, Sipple, the erector. So eventually, we started some of those phasing that we had looked at and poured out. We're going to be pouring out 4 here, but 1 over in here, and that, you know, that takes an interesting impact on line 6, where we kept the shore in for a while. But anyway, it all worked out. So here's a good slide. This really shows, here's the trusses up at the mechanical level, and here's the hangar, and here we are with the column-free space. It's simple diagram. And this is just up in the mechanical level. This Cam's connections. There's still plenty of room for mechanical equipment. There's just an overall view. You can see we're getting close now. The west half is completed, and they're just topping out over on the eastern half. And this is even better. So you can see the temporary shore on the E line, that's been removed because we've poured out floors here. We're all the way up to 4. And then, but over in here, the temporary shores are still in because we still haven't completely topped out the steel. And here's topping out, August 2015, 10 months after bid. And that's the completed project with the drive up and the cantilever. So that's the end of our formal presentation, but we specifically did leave time for questions because it is it's a new process, and so we encourage time for questions. So Bill, do you want to moderate these questions, or shall I take them? All right, sure, right there.
More a question about the design and the construction. I mean, we usually find that deflections that are surveyed are smaller than deflections that are calculated. Is that your experience? 80% or something? Or what it is?
The question was these predicted deflections that we put on the drawings for Sipple to work with. Do we find the questioner's experience is that usually those questions are, usually those deflections may be conservative, overestimated, and what was our experience with that? We decided not to adjust. We put the theoretical, but I would say that the adjustments that we made were on the conservative side. So, in other words, if you heard what Cam said, the adjustments that we made was to members. So like we knew the hangar was going to elongate, so we shortened up on the hangar. So that it would elongate. So like if we had 0.01 inches, we translated that into whatever the nearest 16th of an inch. And then similarly, the truss cord members, if they were going to elongate, they were again shortened. So, but then we had columns that, like that 2P column, the one that's the fulcrum point, we knew that was going to shorten more. So we just elongated that slightly, but anybody that's done a high rise is, I mean, the number, after we did all these complicated computations and phases, it's really 1/8 of an inch per tier, not what we used to use on high rises anyways.
Yeah, I would say you're probably talking about maybe trusses or something, where you get, so I would say that in a normal truss, you might have tertiary and secondary restraints that are helping you perform a little better than your model anticipated. Again, I would go back to a very elegant design that probably behaves like pins. And if you think about those connections, there's a lot of ductility there. You don't have a lot of unpredicted restraint in those connections. It's all just tension and compression and very little, follow-on additional restraint that you would have in a truss system or even in a beam column system where you have some shear connections that are not really shear connections, not pins.
So you found that the theoretical...
Very close correlation. Yeah, we're within 3/16 of an inch, which I would say is... the other thing is the loads are variable too. I mean, the concrete guy is placing concrete with stickers. You don't really know the exact depth volume of concrete you put up there.
If you went to the 111, I don't know if you went to the 111 South Main presentation yesterday, and it's this job on steroids. You're hiring a 24-story building with two-way roof trusses. They spent quite a bit of time doing analysis on that because their connections were so heavy, and they did finite element models of the connections. Our connections were fairly traditional, and I don't think they contributed a lot to the overall deformations.
Thank you.
Yes.
Actually, a question for each one of you. For you, did you know it was going to be a design assist and did that affect your fee? And for Cam, how'd you win the bid?
So the question is to the engineer, did we know that the project was going to be design assist at the time that we were proposing on it? The answer is no. And then the follow-up to that is, how did it affect our fee? When we made the proposal on the project, we did anticipate that it would be an early steel package, and we're in the habit of adding a line item if we do have an early steel package, and not so much for producing the package, it's for all the changes we have to make after we issue the package. So frankly, it was nice to have that buffer because, that the biggest amount of extra work that we did didn't have so much to do with design assist. It had to do with the solution. And, all those drawings that we did that had the deformed shapes and the temporary shoring loads and the line D axial loads, there's work in putting those drawings together and keeping them updated. But, I would say that this project, besides being a very successful collaboration, was also, for our office, it was very profitable.
So the question to me was, how did we win the bid? So we've done design assist projects before. We had some idea of what that was all about, but there's definitely an unknown there. And so for us to make the job profitable, we have to account for enough money in that contract to do that whole scope of work. And that scope of work is not necessarily, there's a good set of bid drawings, a good set of front-end specs that outline what the expectations were, but we didn't really know how many hours. So you can't pad your number up too much to cover the unknown engineering costs and overhead costs that are associated with the project. And the project was, on the front end, essentially a hard bid. We gave a number for what was on the drawings. And it was an SD level drawing, and we're getting pretty good, like most fabricators are, at looking at drawings that are still in the development stage and adequately anticipating what's going to be needed to finish the project. I would say that we have assets on staff. We have engineers and detailers and experienced PMs on staff. And I think that is probably at the end of the day, and the erector as well. The erector was a local erector. He knew the customer, and at our final meeting, our final, right before the award of the project, where we sat down and gave a presentation about what we wanted to do on the project, I think that all those team members were present. They all participated in talking about what they wanted to do, and they were all excited about the project. I think the owner kind of caught wind that we were really on board for the job. I honestly know who exactly we were competing against, but I don't know what they brought to it. I know everyone brought presentations, and you had to come in and voice what you wanted to do with the project. I think that's how we eventually successfully got the award.
So it wasn't a little bit.
No, I had the good fortune of being part of the selection team, which was nice. Again, when I told you that the owner was committed, so we didn't have a lot of vote, but we had a vote. And their team, as far as I was concerned, they had the most comprehensive DA proposal. They had mapped out the hours they were going to commit to it, including hours from the erector, and also they had in-house engineering and detailing capability, which some of the others didn't. And like, that is my number one rule on my projects that I'm always hopeful for. I want to work with a fabricator who has in-house engineering and detailing, because they have control of their own fate. Once they start outsourcing it, that's when problems occur. Yes?
On complex jobs like this in the past, there's always been an engineer of record, a structural engineer for the fabricator, and possibly a structural engineer for the erector. Were you able to eliminate any of the structural guys?
I'll let you answer.
So no, we had to have an erection engineer on the erector side, and then I'm the structural engineer for SIPL, and so we had to have all of those players. I think the difference on this project would be we had a much better understanding of what the engineer of record's design intent was.
Yes.
Sounds like we had really good communication between fabricator director on one side and the design team on the other side. And that probably contributed greatly to this success, that uninhibited communication. But the person that you haven't talked about in this process is the CM and the general. How did they fit in this process, and were they helpful, or did they inhibit the process?
The contractor was really good. Turner, they recognize Cleveland Clinic is a huge client for them, right? And they want to do as much work at the clinic as they can. So when the clinic says, "Hey, we want this process, make it happen," they made it happen, and it wasn't like they were 100% committed. So I was so pleased about that, because I know this process works better when we get to collaborate. There's usually people keeping us from collaborating, and you're right. Oftentimes it's the general contractor, but I've had so many experiences with general contractors saying, "We got to get the steel bid set out. It's very, the whole schedule's based on the steel bid. Got to get those drawings out." So we rush and get them out, and then we get into the shop drawing phase. So here is this most important subcontract, right? And it's going to be steel is awarded. And who do they assign to manage it? Usually it's a kid who just got out of school and has never even seen a shop drawing in their life. And now we have to teach yet another person about the structural steel industry. So, but no, we were Kevin Ott was the Turner's project manager in charge of the steel. They were on our meetings every week, and if we needed stuff from people that weren't a part of our core group that was on the design assist, for example, curtain wall, we wanted information about the curtain wall embeds or the curtain wall this or any other trade, he had it by the next meeting. So there was a commitment there.
Yeah, I think that's good if you have a CM that has a long-time customer that they're willing to please with. It's a one-time project. I've been involved in design assist where the CM comes in and they want to drive the train, and they're not capable of driving the train and making those decisions that are really best solved directly between the design team and the steel contractor.
That is because, by definition, they are a construction manager. They don't know how to manage design because they don't know anything about design.
One more.
Yes.
Can you, for Cam, can you tell me, you said, coming out of the project of roughly 3,000 tons, 3,100 shipping pieces. I assume those are shipping pieces. From your initial proposal, what was the increase in your final contract?
So the question was, what was the increase in our initial contract that we were awarded? We had some metrics to identify the size of the project early on, but what did it? We definitely had a increase in our scope of work. The actual material was pretty well outlined because Pete talked about the vibration requirements. At one of the there were several levels of bidding that we had to go through, several rounds, and in one of the rounds that was specifically identified that we needed to get to this 16 pounds a square foot somehow, and we did something in our office to make sure that we had accounted for that weight at some level of the bidding, and that's actually on that graphic we showed the changes in cost. That's one of the spikes on that graphic. I don't have the specific numbers in my head as far as our cost of what went up, but we were able to capture parts of the project that we typically wouldn't. Miscellaneous parts of the project, parts of the mechanical platforms and things that we typically wouldn't do. Those were added into our scope as the job went on. It was identified that it would be best if we did it and not some follow-on trade.
Yes, all the way in the back. Can you speak up, please?
Yeah, from a fabricator standpoint, would you like to see a design assist project on every project or only on certain projects?
So the question is, from a fabricator standpoint, would we want to have design assist on every project? I think the answer to that is probably no, because not every project needs that level of every job needs that level of collaboration. Not every job needs that level of formal documentation, formal collaboration. I think a lot of jobs are packaged as design, bid, build, and they turn into design assist when you have willing participants to the process and willing collaborators. And that's not every project, and that's not every team. But certainly any job that's got specific, if you're at the design, you're in the design level and you're scratching your head about how you're actually going to execute a complicated erection procedure or a complicated fabrication procedure, that's probably a red flag that you might need a design assist partner.
Yeah, I want to add one thing about that and follow up on this gentleman's question as it relates to the general contractor's involvement. You will find variations of this design assist process going on. In fact, it's very common nowadays on almost every project that design assist is being used for the curtain wall. The twist is the GC is charging their sub with holding the line on the value of that contract as well. And that's where the twist comes in. So now Cam's bid on a schematic design set of drawings, and there's 2,700 tons. And no way shall it go up. In other words, so it's not really design assist, it's like monitoring the design so that the cost doesn't go up. And that's a very different process, and it's not going to work. And again, it's because these general contractors don't understand. So yes, all the way in the back. You have to speak up.
Is there any positive or negative involvement with the AHJ in this process?
Any
Positive or negative involvement with the local AHJ?
Building inspector, the authority having jurisdiction. Is that who you're talking about? Yeah, having jurisdiction. I don't recall.
No, there were no issues. The only issue we had with authorities having jurisdiction was when we were working on the pedestrian bridge, and whether or not we were going to have to satisfy AASHTO because we were going over a city sidewalk. We weren't actually going over a city street. And we were going to have to get somebody, a compliant engineer who was AASHTO certified, which we didn't have on staff at La Magic. But at the end of the day, that went away. Yes, sir.
On the fabricator side, you talk about, you mentioned stairs and metal decking. Can you talk a little bit more about how those were contracted? Were they part of your scope? And maybe a little bit about slab edge conditions and coordination?
That's great. That's a great question. So the question was, I talked a little bit about some kind of secondary things that are part of the steel scope that aren't the main frame. For instance, stairs, metal decking. And the question is, can I talk a little bit about how those items were affected by the DA process? So the metal decking was in our scope. That was part of our contract from the very beginning. And from the very beginning, when we got the design drawings, we're thinking, why is this 19 gauge? I mean, that's like always a red flag when you see 30-foot long 19 gauge deck. You know you cannot erect that. You can't shake that deck out without a crane. So we knew very early that that was going to be a target for us to try to capture really schedule. I mean, in order to maintain the schedule, you can't have the crane tied up, shaking out deck. The slab edge condition is a good one. That was an item that the measure. It was a unitized curtain wall system. So LeMessurier very early on said we want an adjustable perimeter pour stop, which is always, that's like the bane of fabricators. That's always something, if you're going to you can't just ship a plate to the field, the erector is going to die during on his schedule. And to create that adjustable item, how do you do that? We came up with a bolted option, a bolted pour stop solution. And actually LeMessurier took our schematic drawings and created a finite element analysis to back up that we could just use TC bolts in that pour stop connection. Now we were only supporting the concrete. We had the unitized curtain wall buckets that have rebar. So really, the mild rebar in the slab is doing the work of carrying the curtain wall system. It's not so much the pour stop itself. But we did incorporate an adjustable perimeter condition on all of the perimeter locations.
Yes, Larry.
When you pulled the shores on that, did that change the plumbing or building?
The deformed shape included having the building slightly in, so we didn't just have vertical. We didn't just have vertical adjustment. We also had horizontal adjustment. Yeah, I'd have to go back to that slide, but yeah, it's slightly in.
I think your bracing accommodated those loads as well, correct?
Yeah, well, it's actually interesting. One of the ways we actually, a small savings, if you recall, we had the core bracing between the B and C line. We had that running all the way up to the roof, and then we had the teeter-totter over there. So we start going through all the analysis, and one of my young engineers comes, and they're showing me the loads and everything. I said, well, why aren't the loads the same in all of these? So why aren't the loads the same? Well, because we had the roof tied back to the next line of core bracing. So the core bracing was sucking up some of that load instead of it being a simple teeter-totter. So I said, well, we solved this problem. We're going to get rid of that bracing. So we actually got a credit for getting rid of that bracing. Yes, sir.
Did the original contract for the fabrication, after SD, envision some kind of reconciliation at the end of the construction documents or an adjustment?
So the question was, during the bid, the pre-award phase, did we anticipate an adjustment at the end of the project to reconcile, the targets to GMPs? I think every job you have to assume that there's going to be a reconciliation at some point when there's an open scope. There's a variable scope that's not totally captured on the design drawings, and so this job had a very intensive paper trail requirement. So with change orders, the way the process worked is we would provide, when we had like multiple options, so at the kind of a schematic level, we had to provide rough order of magnitude pricing for multiple options. And then from that rough order of magnitude pricing, they selected the best alternative, the leading proposal. And then we had to give additional pricing that dialed that number into a real potential change order kind of number. And then we had to actually this was a cost plus project. So we had to back up all of our estimates with cost data. There didn't end up being there was no exchange of money at the end of the project because we did a good job of accounting all the way through. Does that make sense?
But it wasn't openly bid after the construction or anything like that.
Say that again?
It wasn't rebid at the end of construction.
Okay, so the question was it rebid at the end of the construction? And no, there was no rebid.
You said that elections started at the same time 100% CD drawings were issued for the architect.
Yes.
And when did you do bill order? When did you get the shop drawings done? What stage is it under design?
So the question was the architectural drawings were issued for construction at the time we were erecting. So how did we get that all done? So we were working with an accelerated, a flash track project where you're we mill ordered from SD drawings we're like most fabricators, we're really savvy with rolling casting dates. We know when those milestones are, and our purchasing department is tracking that on a weekly basis. So every week, the PMs know if you don't order it on this date, you can't make your schedule. And so we're pretty good about putting our customers on notice and getting commitments to purchase that material. So we were purchasing the material from the minute that it was awarded. We were already beginning that process of making mill lists and checking mill lists. There was that the increase in some of the tonnage on beams, but that happened in a very timely manner. The measure was responsive. You understood the schedule that we were under. And then the shop drawing process was happening. They were still designing the stairwells, and we were doing stair arrangement drawings, and that was kind of a parallel process.
Yeah, so September, October, November timeframe was when these mill orders were being made, and then you saw you have an April delivery for steel. And the CEDs by the architect was 100% in April, May. But the good thing was, again, you've got the general contractor, the fabricator, the erector, all helping you ride herd on the architect. It helps you get the answers you need in order to advance the design. Yes?
What was the impact on the schedule overall for the whole project?
Well, as far as we know, the day I got on the job, Turner had a schedule that they wanted to meet. And as far as I know, once they signed up all their design assist contractors, that schedule was met. There was a phase where I think they got a little behind because of the winter construction. So some of those subtleties that I was describing where they started to want to change the sequence of pouring out the floor was when they caught up. But, they had the grand opening last month, and as far as I know, that was right on schedule for them.
So all through the project, I said before that they were tracking metrics. So the owner was watching the process of the project, and there was every couple of months they would have a much larger meeting where they would go over the status of the project, the status of the budget, and the status of the schedule. And I was unfortunate enough to attend the last one that right before the finish of the steel erection. And that owner was in the room. They had people in the room, and they were ecstatic about the performance of the team. And we were, at that point, I believe we were ahead of the schedule by a nominal amount, that the erection had gone a little faster than we expected.
So they never did a comparison of the traditional?
It's kind of harder to compare two projects, you mean? Like how with a pro forma schedule?
Sometimes you start with a project like this and do traditional procurement, and then say, well, DA might save us this much.
They have several jobs going on at the same time where they're doing 3 different delivery methods, and they're comparing that's not really an apples to apples comparison because they're different buildings. But they are looking at value capture and how you're performing against the anticipated schedule. So those things are being measured, but they're measured relative to the project you're looking at. But in that meeting, the owner, again reiterated that they are a proponent of the DA system. They want to use it more. That is their preferred delivery mode, and this project validated that.
And I think schedule was a huge concern for this client because, in fact, we got this job like several years actually before we started. And because at the time Obamacare was being implemented, a lot of medical projects, if you're in that field, got put on hold because people were trying to get their arms around what impacts is this going to have, on the institutions and so on. So once they finally decided they wanted to go fast. Yes.
This project has a very kind of specific design red flag to approach. On your other experience with design assist, is there certain areas that you look at right off the bat as potential for value engineering, and is there things that you found? Because I find that in some of these bids, it's hard to find real specific things where you can really target and bring a lot of assets.
So I'm assuming you're asking me that. Is that a question for me?
Yeah.
All right. So the question is, this job was an obvious candidate that you need a little bit of assistance at the front end. On a normal project, I think it's a little more run of the mill. How do you find other opportunities to participate in a quasi design assist mode or to capture value for the owner? So that's like the $1 million question, right? The estimators are in my office weekly looking at different projects that we're bidding. Where do you think there's value? And that is an experience thing, and it's hard to really give you a good answer. We are looking to collaborate on every project. So anytime we get a project that's got anything that's a little bit not run of the mill, we're looking for opportunities to work with the engineer of record to find performance enhancements and value capture for the owner. But as you point out, it's really hard sometimes to get creative because you have a good engineer who has a good efficient design, and the building is already pretty tight. It's kind of hard to find those options. I think it's obvious on a job where you have a red flag that you need the help.
Any other questions? Yes.
Did they talk about IPD at all as a delivery method?
So IPD, you mean integrated project delivery? That was, so the question was, did we talk about IPD on the project? That was the acronym of the job. I mean, IPD was what we talked about all through the project.
This is not an IPD because
Well-
you're not contractually bound to each other, right?
Maybe we're talking about two different IPDs. I mean, this owner used that acronym a lot. Maybe they were using it inappropriately. I guess I've never. So you're saying that in that mode, the contractor and the engineer are working together contractually?
Right.
It's financial contract.
Popular in California.
Yeah, we don't.
and it's
Yeah.
popular in the medical field. No, it wasn't a pure IPD, but it was design assist. And like I say, there were multiple trades with that.
It looks like there are any more questions, so I got to get up and say this was like I've sat through a lot of sessions in my career, and this is like a master class. It covered design, detail, fabrication, erection, and working closely with an architect and the owner. This was fantastic. Could you get the PDH code again, Peter?
Okay.
I don't want to get...
first, I have to have my... this was Joe McKendry's reaction to design assist. We've lost control.
Oh, you know what? Here. Try it again.
So after we went through our big session, Joe said, if everybody would just do their job, it'll be fine. So, of course, Simple being from Pittsburgh and us being from New England, we had to start one of our design assist go-to meetings with this slide. And I have my Patriots tie on today, by the way. So at any rate, this was just a summary of the lessons learned. We've already articulated all these, and I certainly encourage you guys to keep pushing this, especially the fabricators, because you probably have more way with the general contractors than we do.
There we go.
So anyway, and then here's our PDH code, 44884. And do any of the architects need the slide that was in the very beginning that had the architect's code, or you're all set?
I think
The architect should make note of the
PDH, that's all they need? Okay, great.
and enter it in the kiosk.
Okay. Thank you very much for attending.